The speed at which AI and DeFi-related technologies are developing is staggering. But as blockchain moves into more privacy-sensitive areas, one big question continues to emerge. How can we protect personal data while maintaining the open, verifiable nature of blockchain? I'm sure no one wants their personal information leaked online and used for criminal or other dubious purposes. But what if I told you that your data might be used for powerful machine learning while remaining completely private and leak-proof? It doesn't sound possible, does it? But it's already a reality. Today, we're going to talk about one of the most complex and promising narratives according to Binance, fully homomorphic encryption. We'll find out how it relates to machine learning and how this whole structure allows calculations to be performed on encrypted data while maintaining its confidentiality. I know this sounds quite difficult, but stick with me and hit that like button now, because by the end of this video, you'll understand why this is one of the most revolutionary advances at the intersection of AI and DeFi. You are on the Octa-Core channel, and let's get started. As you may have guessed, FHEML consists of two parts: fully homomorphic encryption and machine learning. And while you've probably heard of ML and have an idea how it works, it's worth taking a closer look at FHE and trying to explain the essence of what it does in simple terms. Imagine that you own a chest filled with precious gems and gold. The chest is sealed with an unbreakable lock, and only you have the key. Traditionally, if someone wanted to do operations with the treasure, they'd have to unlock the chest and reveal its contents. But what if I told you that with FHE, you never have to unlock the chest? It works as a non-transparent matte black glove box. Glove box allows random people to touch the treasure, do some operations with it, like placing the gems differently. And you, as the owner of the treasure, once you unlock the chest, will be able to see the results of those operations. All without ever opening the chest and without possibility of taking anything away. The lock remains sealed and the contents completely hidden. This is the magic of FHE, the ability to work on encrypted data without decrypting it. It means that sensitive information, like your treasure, remains completely secure, private, and untouchable, even while complex calculations are being performed on it. So fully homomorphic machine learning is a way of implementing ML algorithms that use FHE schemes to perform computations on encrypted data, ensuring its privacy and confidentiality. FHE wasn't just discovered overnight. It's the result of decades of research in cryptography, with several key innovations that laid the groundwork for what we have today. The concept of FHE first appeared in late 1970s. Early implementations like partially homomorphic encryption, PHE, allowed for limited operations, restricting its utility to specific scenarios. Over time, somewhat homomorphic encryption, SHE, was introduced, which permitted more operations, but with limits. The key problem was that noise in encrypted data would accumulate with each operation, eventually requiring decryption, which didn't allow for fully flexible, secure computation. The real breakthrough came in 2009, when Craig Gentry proposed the first feasible, fully homomorphic encryption scheme. Gentry's FHE allowed an arbitrary number of operations, both addition and multiplication, on encrypted data while keeping the underlying information secure. This was revolutionary for secure data computation, but initially suffered from inefficiency, being millions of times slower than unencrypted computations. Since then, significant cryptographic methods and hardware advances have greatly improved FHE's performance, making it a viable option for real-world applications. The evolution of FHE from PHE and SHE to fully homomorphic schemes showcases the persistent innovation driving modern cryptography. While once considered a distant ideal, FHE is now becoming more practical, especially in areas like privacy-preserving machine learning. The FHE workflow is as follows. First action, key generation. FHE begins with generating a pair of keys, a public key for encryption and private key for decryption. This is done using advanced mathematical structures like lattices that are hard for traditional computers to break. Second action, encryption. The data, also called plaintext, is encrypted using the public key. Plaintext is transformed into ciphertext through complex mathematical operations. The ciphertext is indecipherable without the private key, making it secure for processing. Third action, evaluation. This is where FHE's magic happens. On the encrypted data, ciphertext, certain operations can be performed without needing to decrypt it first. These operations are usually limited to additions and multiplications. For machine learning, it means that models can be trained or predictions can be made on encrypted datasets. Fourth action, noise management. During computations, FHE ciphertext accumulates noise, an inherent issue in encryption schemes. Too much noise can make the data unusable. Advanced FHE schemes incorporate noise correcting techniques to control this buildup, ensuring computations remain accurate. Fifth action, decryption. Once the computation is done, the result is new ciphertext. Using the private key, the result is encrypted back into plain text. The decrypted result is identical to what would have been obtained if the operations were performed on unencrypted data. In general, fully homomorphic encryption can be categorized into two types, word-wise and bitwise. Word-wise FHE operates on larger units of data, such as entire ciphertext blocks or polynomials. This type is ideal for tasks involving arithmetic operations. Bitwise FHE operates on individual bits. This type is ideal for operations that require exact precision. In addition, there are currently quite many FHE schemes for a variety of tasks. Their utility is differentiated by their core operations and mathematical underpinnings. Fully homomorphic encryption machine learning and zero-knowledge learning machine (ZKLM) are both privacy-preserving technologies used to protect sensitive data during machine learning computations. While they have similar goals, they also have differences. First, cryptographic mechanism. FHEML preserves data privacy during computation. It does not guarantee computation authenticity. ZKLM focuses on proving that computations were authentic and performed correctly, without revealing the underlying data, but not all of it. Second, compatibility with Ethereum virtual machine. FHEML is compatible with EVM and Solidity language. ZKLM is incompatible with EVM and Solidity. It requires a new language for creating contracts, such as Cairo. Third, applicability in DApps. FHEML has arbitrary logic for a wide set of DApps. ZKLM has limited logic for a limited set of DApps. For increased security and efficiency, FHEML can be combined with other latest tech solutions. For example, FHE can be combined with zero-knowledge proofs to achieve both confidentiality and computational authenticity. FHE can also be combined with multi-party computation, or MPC, to address the efficiency issue. If the data can be sharded, then computations can be run simultaneously on many servers, mitigating the performance problem. Another use case for FHE is the coupling of this technology with a trusted execution environment, or TEE. In contrast to the cryptographic approach, the hardware-based solution implemented by TEE doesn't add any additional computation, but simply moves the original computation into an isolated environment within the CPU. By implementing TEE in key generation and data decryption, we avoid significant performance penalties. This creates a more secure and efficient environment for managing FHE keys. Currently, fully homomorphic encryption faces a number of issues that are being addressed. They can be divided into three types. One is technical performance challenges. Currently, FHE EVM speed is around 5 transactions per second, compared to Bitcoin's 7 transactions per second. Solution: active performance enhancement through hardware acceleration, software optimization, algorithms, and other latest tech. 2. Regulatory and legal challenges. Blockchain with strong privacy features can face regulatory scrutiny and legal barriers. Solution: the projects may need to allow governments to access the information if necessary, by thinking of relevant entities or through certain privacy compliance technologies, if there is a court order. 3. Listing challenges. Privacy tokens, such as Monero, have been delisted from all major exchanges, while protocols with optional privacy features, like Dash and Zcash, remain listed. Solution: project can have optional privacy features instead of full privacy, with support for both private and non-private transactions. Fully homomorphic encryption is reshaping the future of DeFi by enhancing privacy, security, and functionality across a variety of applications. In DeFi, the ability to process encrypted data without exposing sensitive information has opened new horizons for private transactions, secure integrations with other narratives like decentralized physical infrastructure networks and decentralized science. Also, if you haven't seen our Deep In video yet, you should definitely watch it. There is a lot of interesting stuff in it. FHE real use cases include privacy-preserving AI, data security in the use of AI for collaborative data analysis and model building without violating privacy, dark pool, protecting trading information on DEXs and preventing price manipulation and data leakage, private DeFi, conduct transactions and invest in digital assets without revealing personal information, private voting in DAOs, NFT blind auctions. FHE vector database ensures secure storage of sensitive data while allowing users confidential access through private requests. Private software, Solidity and other libraries for developing private smart contracts that operate on encrypted data, and SDK for building dApps to properly encrypt data and interact with the encrypted blockchain. At the moment, the FHE ecosystem in DeFi is not very large and most of the projects are still in the development and testnet stage. FHE can therefore be provisionally divided into general tools. Zama is homomorphic encryption toolset that allows developers to process data without the need for decryption. This technology enables the creation of private smart contracts on public, permissionless blockchains. With Zama's tools, specific users can access transaction data and contract states while maintaining privacy and security. Zama has raised $73 million in Series A round. FHEML is developing an open-source library of FHE components to ease application creation and bolster privacy in the Web3 domain, aiming to secure a privacy-centric foundation for Web3 and uphold privacy rights universally. FHEML has raised $1.4 million in pre-seed round. FaireBlock is the HTTP to HTTPS solution for blockchains, which delivers a permissionless, compliant, and lightweight approach to enabling multi-party computation and encryption within every protocol, beginning with threshold identity-based encryption. FaireBlock has raised $2.5 million in the pre-seed round. L1 Blockchains. Secret Network is a blockchain platform that provides privacy-preserving smart contracts. Blockchain launched in 2020, it operates as a privacy-focused project and is currently one of the central blockchains in the Cosmos ecosystem. Secret Network 2.0 will use a multi-party computation variant of FHE called Threshold FHE for validators. Tiro is a general-purpose, private and scalable L1 blockchain that allows developers to deploy powerful and unstoppable applications, while users retain total control over their assets with complete privacy. The project is already running in mainnet and plans to introduce FHE in consensus soon. Inco is a modular, interoperable Layer 1 blockchain network focused on bringing confidentiality to decentralized applications. It can be compared to modular blockchain projects like Celestia and Lava, which focus on data availability and data access respectively, while Inco concentrates on confidentiality. Inco has raised $4.5 million in seed round. L2 and Layers. Phoenix is a confidential L2 blockchain powered by fully homomorphic encryption. Through the usage of fully homomorphic EVM, Phoenix enables Ethereum developers to seamlessly build encrypted smart contracts and perform encrypted computation of data, all while using Solidity and other familiar, easy-to-use tools. Phoenix has raised $25 million in 2 funding rounds. Mine Network, the fully homomorphic encryption restaking layer for AI and proof-of-stake networks. It accepts restaking tokens from Ethereum, Bitcoin, and AI tokens, operating as an FHE validation network. This project enhances consensus, data integrity, and cryptoeconomic security for decentralized AI, DePIN, EigenLayer, Babylon AVS, and many other proof-of-stake networks. My network has raised $12.5 million in 3 funding rounds. Rivals Network is an AI intelligence layer designed to monetize personal data, allowing users to earn based on their credentials through an AI-powered data and attention economy. The project aims to provide a secure method for AI companies and agents to access and use data through FHE and other privacy-preserving technologies such as ZK, TE, and MPC. Rivals Network has raised $11.6 million in several funding rounds. Hardware for acceleration. Optalysis is a hardware project which builds next-gen computational processing power that enables the analysis and computing of fully encrypted data. The project has several products that facilitate the creation and operation of FHE-based proof of concepts in a simple and secure environment. Inganyama is a next-generation semiconductor company focusing on zero-knowledge proof hardware acceleration. Using a broad multidisciplinary approach and a deep understanding of the ZK landscape, they focus on finding and solving computational bottlenecks in ZK proofs. Ingonyama has raised $41 million in 2 funding rounds. Chain Reaction is a pioneering project at the forefront of advancing blockchain and privacy technologies. With a focus on accelerating compute performance, the project empowers companies to address complex global challenges like FHE by adapting and scaling innovative solutions. Chain Reaction has raised $70 million in Series C round. FHE with AI. Privacy is a decentralized AI network that leverages FHEML for secure data circulation. It utilizes distributed computing resources for FHE AI operations supported by Zama's concrete ML technology. Also, the project develops proof-of-human concept technology that attests your human liveness to protect your digital presence from bots and AI impersonations. Site AI is a computational oracle that allows users to delegate computations on encrypted data using FHE powered by Zama. Based AI is a decentralized blockchain platform designed to address data privacy and security challenges in AI applications. The integration of FHE with LLMs leads to the development of zero-knowledge large language models, which represent a notable advancement in combining distributed computing with artificial intelligence. Privacy protection is extremely important in Web3, and FHEML tech represents a revolutionary leap forward for DeFi in terms of both privacy and computational capabilities. The mere ability to perform computations on encrypted data without compromising security will redefine how we handle sensitive information. As DeFi continues to evolve, the integration of FHEML with advanced narratives such as AI, DePIN, ZK, DSCI will unlock a new era of innovation. This powerful combination will enable the creation of cutting-edge scenarios, products, and services while ensuring the highest levels of security. Thank you for watching the Octacore channel. We'll continue to monitor the latest news and insights in DeFi and AI, and please don't forget to subscribe and like this video. See you soon.